Hi friends, good morning. Welcome back to another session from Design of Compression Members, Steel Structures subject. So today we'll start another new topic, that is analysis of angle struts. Okay, analysis of angle struts. Okay, what is a strut? It is a compression member. If you can see these struts in case of a trusses, roof trusses. Now when I consider this strut, okay, there may be of single angle, okay, and a double angle, single angle or double angle. Coming to the single angle, there may be continuous or discontinuous. Okay, continuous or discontinuous. In that you will be having case 1, case 2. Means based upon the loading criteria we will be deciding case 1 and case 2, and here case 3. Next one is what? Case 4. Here what is case 1 means? Single angle means axial load. Next one is non-axial load, means eccentric loading. Here axial loading means what? Loading through both legs, loading through both legs comes under case 1. Now why we are differentiating different as a case 1, case 2 means the way of calculating determining the strength will be differing. Okay, next, loading through only one leg, loading through one leg. Okay, now here in a single angle you may come across case 1 and case 2 in both continuous and discontinuous, whereas in double angle case 3 discontinuous and case 4 continuous. Now why we are differentiating means you will be calculating the effective length differently. If I take this case 3, again you will be having two parts. Okay, that is angles on same side of gusset plate, same side of gusset plate. Next, here in this case angles on either side of gusset plate. Now same side of gusset plate means I can draw the rough figure. If this is a gusset plate, like this the condition. On either side of gusset plate means if this is a gusset plate, like this the criteria will be, right? Now when this is on same side of gusset plate, you will be having only effective length, one effective length, that is effective length equals to actual length. And when we have on either side, you will be having with respect to ZZ and with respect to YY. With respect to YY you can take L effective equals to YL, whereas here 0.7 to 0.85 times of L. Okay, while solving the problem it will be very easy for you. Okay, and here in case of a continuous double angle continuous section, in that KLZ will be equals to KLY. Okay, that is you can take 0.7 to 1 times of L. Very easy problems. These are only conditions are n number, but 3 types of problems will be arised here. Okay. Now see here, I will explain you clearly. For this case 1, single angle axial load means loading through both legs. Now how the procedure to analysis is the same thing what we done previously for I section, means the procedure is same as for I section, axially loaded column. Okay, whereas in case 2, that is non-axial load or eccentric load are loading through one leg, then in that case you are supposed to follow one, that is equivalent slenderness ratio. This is as per another clause 7.5.1.2. okay, equivalent slenderness ratio. Next we'll see the procedure later after this complete explanation, and what will be changes in this one, right? Coming to double angle discontinuous member, in that angles connected to same side of gusset plate. Okay, the design will be same as single angle connected to gusset plate through one leg. Okay, next angles connected on either side, this is the effective length, and the design will be same as, means this one and this one will be same, this case 1 and I section, and this, the design will be same. Okay, next double angle continuous, this also same as this one, means this one will be same, similar to as that of I section. What is the I section we done? We have calculated H by BF ratios, effective length calculated, decided the buckling class, calculated the effective slenderness ratio. What we done, the same procedure will be holds good for here, this one. Okay, whereas here it will be changing for case 2 and okay. Now we'll see in detail regarding the what case 2. Okay, what is case 2? Single angle strut, okay. Now the flexural torsional buckling, I will use code book now, IS 800 2007. The flexural torsional, okay, buckling strength of single angle, okay, loaded with compression through one of its length is calculated by the formula, that is equivalent slenderness ratio. Now we'll see what is this equivalent slenderness ratio. as per clause 7.5.1.2. I will write the page number once it opens. Meanwhile, I will write it is denoted by lambda E. Slenderness ratio means lambda, equivalent means lambda E. Okay, which is equals to under root of K1 plus K2 into lambda Vb square plus K3 into lambda phi square. Okay, right, as per see 7.5 angle struts. Okay, single and struts. Next, single angle is considered loading compression. Now loaded through one leg. Loaded through one leg, lambda equals to under root of K1 plus K2 into lambda Vb square plus K3 into lambda phi square. Okay, now K1, K2, K3 depends upon end conditions you will be calculating. Okay, I will show you. So this one K1, K2, K3 fixed T conditions depends upon what? End conditions. From what? Page number 48, table 12. Now you in this formula you got K1 value, K2 value, K3 value from table 12 of page number 48. Now what is lambda Vb square? Okay, here you got a formula for lambda Vb, where lambda Vb equals to what? L by RVB by under root of pi square E. It is not epsilon, it is E by 250 into epsilon. Okay, in this revised version you got E here. Okay, next what is lambda phi equals to B1 plus B2 by 2T by epsilon into under root of pi square E by 250. Okay, now where L is nothing but center to center of the supports, radius of gyration about the minor axis. You can obtain this value from where? Steel table. And B1, B2 is nothing but width of the two legs. Suppose 90 by 60 by 10 mm say for example. So 90 plus 60 by 2 into 10, like that you will be substituting, where epsilon equals to 250 by Fi to the power of 0.5. 250 by Fi to the power of 0.5. All these are there. No need to write again separately, but for our practice we are writing. So this will be available in your. So while you are going to calculate the angle strut, analysis of angle strut, please remember page number 48 of IS 800 2007, which is very important. This is the, once again I am repeating, equivalent slenderness ratio K1 plus K2 lambda Vb square plus K3 lambda phi square, where K1, K2, K3 are available from table number 12. It depends upon the fixity conditions. Now here see, when we are dealing with the welded connections, okay, so bolt will be of say some 10 mm 12 mm dia. So number of bolts for a length of weld will be definitely more than 2. Means you neglect this one, you only consider the top two. Means this is particularly for bolt connections, but we are dealing in our curriculum as per welded connections. So based upon that one, so welded connections for a length, particular length will be definitely, means if I do a weld of this much in that area, definitely more than 2 bolts will be available, right? So that is the reason we will be taking this one. Okay, this is what regarding the equivalent slenderness ratio. Okay, once you get lambda e value, okay, once you get lambda e value, then what you have to do? You have to equate this lambda e to non-dimensional slenderness ratio. Okay, after substituting everything, after calculating this one, you got lambda e value. This should be equated to what? Equated to non-dimensional slenderness ratio lambda. Now where you can obtain this lambda means just from clause 7.1.2.1. okay, that is here in this case yes, here it is. See, from page number 34. Okay, this is what lambda non-dimensional effective slenderness ratio means. Lambda equals to lambda e, which is equals to, what is the formula? Under root of Fi into KL by R square by pi square E. Okay, you will be getting what? KL by R value. Means this is the way you are supposed to calculate the effective length. Now once you got the effective length, okay, what you have to do? You visit always table number 9C. Why I am saying always 9C? Means any built up section or angle section, it is buckling class C only, as per table number 10 of page 44 IS 800 2007. What it gives is, what it gives, any angle section. Okay, I will show you here. See, as per table number 10, this is table number 10. See, these are the angle section, channel section, T section or built up section. Angle, channel, T section, solid. What is this one? Buckling class C. So after, from here, from this, after equating effective equivalent slenderness ratio with the non-dimensional slenderness ratio, okay, you will be getting KL by R. Okay, for this particular KL by R value and given Fi value, you visit table number 9C. Then what you will be obtaining there? You will be getting FCD value. What you will be obtaining? FCD value. For that particular FCD value, okay, the design strength will be equals to FCD into area given, area of the section given. You will be getting the design strength. This is the analysis procedure. Okay, right? Now we'll try to solve one or two problems based upon this one. Is it okay? Now we'll try to solve one problem, that is determine the design strength in compression. Determine the design strength in compression of a single angle discontinuous strut ISA 90 by 60 by 8 mm of length, okay, 2.5 meters, is connected to a gusset plate, okay, through its longer leg by fillet welds. Take yield stress of steel as 300 MPa Newton per mm square, and modulus of elasticity, even though if it is not given, it is constant, that is 2 into 10 power 5 Newton per mm square, okay. And assume the fixity condition, gusset fixity condition as hinged, okay. Now what is this continuous and discontinuous member? Okay, if it in a member edge to edge there are no separate suppose if you take a high tension wire towers, high tension towers, in that you will be having compression members which are discontinuous each other, okay. Like that particular compression member you will be having continuous. Suppose if I take a truss, okay, if I take a truss, okay, now here strut and here it is, this is a principal rafter. Now for a principal rafter, this is completely principal rafter which is continuous with a number of what, supports, whereas this is a strut, this is considered as a, whereas only edge to edge you will be having two supports and no other is there, that is nothing but what, discontinuous, and this is continuous, okay. Now we'll try to solve this problem. It is very easy, only formula based, it is somewhat difficult to see. Now here in this condition, hinged, effective length equals to actual length equals to effective length, that is 2.5 meters, so 2500, gusset plate, longer leg connected, this is 90 and this is 60, sorry, this one also should be like this, okay, 8 mm, okay. Now what is the fixity condition? Hinged. So from table 12, page 48, okay, fixity condition. Now we will go for so see here, fixity condition hinged, okay. Now what is K1, K2, K3 values? K1 0.7, K2 0.6, K3 5, okay. Now right, next first we write the formula, then we'll come across lambda equals to under root of K1 plus K2 lambda Vb square plus K3 lambda phi square, okay. Now already section is given 90 by 60 by 8 mm, okay. For this you once visit SP6 chart, okay. From that what you can obtain? Area, like that, right? So what is this? This is I section, means still if you go you will be getting channel. Next only what are those? Angle section. These are channel sections. Yes, angle sections. What are these? Equal angle. We require unequal angle. Unequal. I required. Yes, unequal angles. What is the size? 90 by 60 by 8 mm. 90 by 60 by 8 mm. Okay. Now what is that 90 by 60 by 8 mm area? It is area equals to 1137 mm square. Now while calculating lambda Vb, you want RVb, that is minimum radius of gyration. So here 90 by 60 by 8 mm. Now if I go for next page, see 90 by 60 by 8 mm, this line. Okay, second line. Actually this is a two-sided book. Okay, right. Here if you can see radius of gyration, RXX and RYY, RVV, this is RVV. Now how much it is? RVV 1.28 centimeters. I want in mm. So RVV, that is R minimum, is equals to 12.8 mm. If you can see these things, this is minimum, right? So still anything is required? No. Right. Now first we calculate epsilon equals to, okay, 250 by Fy to the power of 1 by 2. What is 250 divided by Fy is given as 300 divided by 1.2. Okay, so 250 divided by 300 to the power of 0.5. So how much you are getting? 0.912. Now everything is ready. Next we will calculate what? Lambda Vb. First, what is the formula of lambda Vb? Once we visit IS 800 2000, page number 48. Okay, 48, right. Now see here, what is the formula here? Actually this light is getting disturbed because of this brightness. L by RVB by pi square E by 250, and lambda phi equals to B1 plus B2 by 2t by under root of pi square E by 250. Okay, right. Now first we'll try to solve this one. I will keep this aside. Okay, now what is this lambda Vb? L 2500 divided by 12.8, L by RVB by, what is epsilon you got? 0.912 into under root of pi square into E 2 into 10 power 5 divided by 250. If I solve this one, pi square, okay, into 2 into e power 5 divided by 250, so denominator it is 81, 2500 divided by 12.8, it is numerator 195.31, okay, divided by 81, so 2.41. This is lambda Vb square. This is we calculated lambda Vb square. Next, lambda phi which is equals to B1 90 plus B2 60 by 2 into 8 divided by epsilon 0.912 into root of pi square into 2 into 10 power 5 divided by 250. Okay, so see here in the denominator this one and this one, and see means this is 81. So b plus b1 plus b2 90 plus 60 divided by 16. 2 into 8 is 16. So how much it is? 9.375. Okay, 9.375 divided by 81. So you get 0.115. So you got lambda Vb here and lambda phi, and you got everything k1, k2, k3. Substitute here. Therefore lambda E equals to, what is the formula? K1 plus k2 into lambda Vb square plus k3 into lambda phi square. Okay, now if I substitute here, what is k1? 0.7 plus k2 0.6 into lambda Vb you got as 2.41 square plus what is k3? 5 into 0.115 square. Okay, so 0.6 into 2.41 square, 0.7 plus 3.48 plus 5 into 0.115 square, 0.066. Okay, now 0.7 plus 3.48 plus 0.066, root of answer. So how much you got? 2.06. Okay, this is lambda E. As per our procedure, now equating lambda E with non-dimensional effective slenderness ratio. Non-dimensional effective slenderness ratio. Okay, that is what? Lambda equals to Fi into KL by R square by pi square E with whole root. Now that is, we are supposed to equate like this. Now what is lambda E value? 2.06 equals to under root of, I know 300, Fi as 300. Okay, KL by R square by pi square into, okay, 2 into 10 power 5, right? So before solving, we'll do it squaring on both sides. Okay, what we do? Squaring on both sides. Now while doing squaring on both sides, what happens? This 2.06 square equals to 300 into KL by R square by pi square E, you remain with. Okay, now in that KL by R square equals to, okay, 2.06 square into pi square into what is E? This cross multiplication, 2 into 10 power 5 divided by 300. Okay, now if I substitute KL by R square equals to, what you will get? 2.06 square into pi square into 2 into e power 5 divided by 300. You got 27921.76. Okay, now KL by R equals to, okay, root of 27921.76, which is 167.0 what? This is KL by R. Once again you see this step, we got the conditions. Based upon the conditions we got K, K1, K2, K3 values from table number 12. Okay, from that you got 90 by 60 by 8 mm. You calculated, taken the area and minimum radius of gyration from the steel table. These two values are from steel table or SP6 chart. Okay, and we have elaborated the formula, and we calculated epsilon, and we calculated lambda Vb and lambda phi values. Substituting here you got lambda E, equivalent slenderness ratio value. So after getting this one, now we have equated that with non-dimensional slenderness ratio as per this formula. This is page number 33 of IS 800 2007. Okay, after solving everything, you got equivalent slenderness ratio 167. Okay, next now from previous page we got KL by R as 167. Now deciding the buckling class, what we decide, that is from table 10 page number 44. Okay, any angle section, any angle comes under buckling class C. So design compressive stress, FCD can be calculated from table number 9C. Okay, now FCD from table number 9 means for KL by R and FCD for particular Fy as 300 MPa. What is KL? You got 167, means it lies between 160 and 170. So here right, this is see, this is table number 10. In that, what, this is the angle section. Okay, so angle section, it comes under what, buckling class C, right? So from table number 9C and particular 300 F yield stress, and it lies between 160 and 170, means for 160 this is 54.8 and it is 49.3. These two values for 300, this one, see, 160 and 170, right? So we'll do interpolation. 54.8, from here to it is decreasing, so minus of 54.8 minus 49.3 divided by 170 minus 160 into, we have taken first as this reference, so 167 minus 160. Okay, so 54.8 minus 49.3, divided by 10 into 167 minus 160. Okay, so 54.8 minus of answer, so you got 50.95 Newton per mm square. Right, now design compressive strength, okay, which is PD equals to AE into FCD. Okay, so what is AE from what? 1137 mm square, that is 1137 mm square into FCD you arrived as 50.95. okay, so 1137 into 50.95. okay, so how much you are getting? 57,930.15 newtons or 57.930 kilo newtons, I think. Yes, so this is the problem. Now what is the difference between the previous problems and these problems? Previously what we done in the earlier problems in the analysis, if you go back, see here for a non-built up section we'll see, just to know the difference. Okay, now see, an I section is there. For that we have written the properties from the steel table, and first we calculated effective length based upon table number 11, page number 45. In that, based upon this one, you have decided the buckling class. While deciding the buckling class, we have chosen the section, how H by BF ratio values we have calculated, right? So while calculating this one, you have come to an arrival that you have decided the table about ZZ axis and YY axis. So you have visited table number 9A and 9B for particular these sections. After that, calculated effective slenderness ratio about both the axes, and okay, next about ZZ axis and about YY axis you have calculated the FCD values. Okay, now after that the minimum value multiplied with the area, you got the it's a strength. Coming to today's problem, it is totally different. That is I section, which is used as a what? Compression member. This is an angle strut member. Okay, in this is the procedure. After doing this much of procedure, what you are getting here is what? Effective length. What you are getting? Effective length. See, this is the equivalent slenderness ratio value. You are calculating K1, K2, obtaining K1, K2, K3 values from table 2, well, page number 48, based upon the fixity condition. Fixity conditions are either it may be hinged or fixed. After getting that, you are going to calculate every terminology in this one to obtain the equivalent slenderness ratio. So you have arrived with the effective length, equivalent slenderness ratio. Okay, so you got this one. To this one, this is a non-dimensional parameter. Slenderness ratio is nothing but it's a ratio, no dimensions, no units will be there. Okay, to that one you are equating with the non-dimensional effective slenderness ratio. Okay, that is we are considering lambda E as lambda, which is equals to, this is the formula from page number 33, 7.1.2.1. so what you are doing after equating, from that you are going to get the scale by R value. What is the scale by R value? Again it's a slenderness ratio. How we have calculated? See, first we are removing this root. For removing this root, you have to square on both sides. So while squaring on both sides, you will be getting a square, this one. So on calculation, you got KL by R value is this one. Okay, Later we have visited table number 9C particularly, because as per table 10 what it decides is any section, either it may be a built up section or a channel or an angle or anything, it is buckling class C. So for that reason 9C you calculated FCD based upon the KL by R values for a particular Fi. So interpolation, you got this one, multiplying that FCD value obtained with the area, you got the design strength. Okay, so in the next further classes we'll solve more problems on this particular topic. Thank you for watching.